Good evening. My name is Edward Washroom, the tutor in Edward's Academy. This evening, I will actually bring to you an interesting topic in econometrics. We are going to discuss about what we call the ARIMA methodology. The ARIMA methodology, we are going to talk about how to forecast using the past value of dependent variable over time. And the learning objective in this class this evening will be to actually learn how to identify an ARIMA model, estimate an ARIMA model, diagnose ARIMA model, and make forecasting. But to achieve that feat, it's expected that we look at the theoretical section of the ARIMA before delving into the estimation proper. So this class is going to be subdivided into three phases. The first phase will talk about the theoretical section, which I'm going to address now. In the second video, I will present identification and estimation. In the third video, I will present diagnostics and forecasting. Please stay tuned to my channel as we look at it as a family. Introduction. In econometrics, the least square assumption explains either the regression or correlation of one variable on another with little attention to previous values of the dependent variable in what is known as the autoregressive models. But in real life situation, you can only predict the future behavior of a person if you know his or her previous value. And dealing with one individual variable is known as univariate analysis, while dealing with more than one person or individual is known as multivariate analysis. The ARIMA methodology was actually put in place by Boss and Jenkins in 1976, and the ARIMA process is a univariate estimation that allows the researcher to predict or forecast the future value of a variable using its present and the previous value. The past value of a variable or a person is known as this lag behavior or the lag value of that particular variable. The ARIMA process can be decomposed into the following components. We have the ARO components, the integration component, and the MA component. The ARO component is also known as the autoregressive component. It deals with the past value or lag value of the dependent variable used as an independent variable in the same equation. In such a situation, the dependent variable is said to have autoregressed itself. Just like what we have in this equation, we have yt as a function of alpha 0, the autonomous component, alpha 1 yt minus 1 plus ut. And this estimation, this is the normal estimation of an autoregressive model where the dependent variable we actually autoregress itself, but the lag value of the dependent variable, not the dependent variable itself. The second equation will have the first and the second year lag value of the dependent variable autoregressing itself. The third equation you are seeing here is the same thing as the first equation, but just a representation of it. So when the previous behavior of a person is used to predict the present behavior of that person, that what we are seeing here, the yt minus 1 is the previous value of the yt, so it's used to predict the future value of the present value of the yt rather. Then in the moving average section, we have the MA. The MA is a moving average, and it has to do with the use of the error term. The error term is always known as the UT. The UT is the error term. When the previous value of the error term is used to model the present value of the error term, at that level we say that we actually have modeled a moving average. Like what we have in this equation, we have the UT is a function of alpha 0 plus alpha 1 UT minus 1. This is a moving average equation because the UT is a function of its previous value and values rather. We have UT minus 1 and UT minus 2. This can also be represented in this form. So if you sum the ARO and the MA together, we have the AMA. The AMA is the summation or combination of the ARO component and the MA component, like a component as we can find here. This is equation, the first equation the AR equation, while this is the MA equation. So if you sum these two equations together, you are actually going to arrive at what we have here. This is the ARIMA component. But for you to actually use the ARIMA component, the variable must be integrated. So you must subject the time series variable into a unit root process that will actually be integrated. So when this particular series is being subjected to a unit root process, then the I involved in it, or the I that is in between the AR and the MA, is integration. So once it becomes integrated at order 0, at that level, the series is actually good for an ARIMA estimation. So the word ARIMA was conceived because the ARIMA was not stationary. Therefore, the raw data are subjected to differencing or the trending. Therefore, after subjecting the data to a first differencing unit root text, it becomes stationary. On that premise, the ARIMA process will now commence. So basically, it's expected that the time series data you are actually going to be using in this particular process will be stationary after first differencing. Most of the time we use the ADF, the Philip Perron, the KPSS, and host of other tests of unit root text. So if you find yourself in this situation, this is how we look at the three components in ARIMA model. In my next video, I will do a practical explanation of how you can estimate an ARIMA, identify an ARIMA model, then estimate an ARIMA model, then before talking about diagnostics and forecasting. Thank you for listening to this very short video. In the next video, I will do what I have just said. Please stay tuned. God bless you.